So, picking up where we left off, 11.7, so a couple of division problems. So if we've got, for example, the division problem 5 divided by 2i. Recall, and on your exam, this is number 14 and 15. So if you scan back in your exam, did everybody get their exam back? Okay. So numbers 14 and 15 in your exam, the directions were to rationalize the denominator. Now, rationalize the denominator means this is like a division problem, or you could call it a quotient or a division problem. We're just really calling it a quotient. Rationalizing the denominator means there's a denominator and it has a radical in it, and we do not want radicals in our denominator. So in order to get rid of a radical, our skill is to multiply it by itself. If we have a single radical in the denominator, we just multiply it by itself. If we have a radical binomial, a binomial that includes a radical, then we multiply by its conjugate. Okay? Either way involves multiplying a radical times itself, and therefore it kills the radical. Now, a lot of people wanted to multiply the top and bottom by 3 square root of 10. And that's fine. That's mathematically correct as long as there's a 3 on top and a 3 on the bottom. No problem, except then you end up with bigger numbers, and I don't know that there was anyone who did that, maybe one person that did that. Most everybody who did that got it wrong. Might have even started off right, but then kind of went off the rails. You're dealing with bigger numbers, there's more to simplify, it's easier to get lost. So it's not mathematically wrong to multiply by 3 times the square root of 10 as long as you do it on top. Just, I don't recommend it. Because your goal is to kill that radical, and all you need to do to kill that radical, the bare minimum you need to do is multiply it times the square root of 10. Now what that means is 3 times the square root of 10 times the square root of 10. And what is the square root of 10 times the square root of 10? 10 times the 3, and therefore this will be 30. Now if you multiply times 3 square root of 10, then you are multiplying 10 times the square root of 10, square root of 10 times the square root of 10, which is 10, times 3, which is 9 times 10, which this would be 90. Okay. So that's mostly where people went wrong. They multiplied 3 times the square root of 10 here, but then they only used 1 3 instead of 2 3s. Okay. So just as keep it as basic as possible, this would be 30, and this would be used by our product rule, the square root of 2 times 10, or the square root of 20. Now it needs to be simplified from there. Square root of 20 breaks down into the square root of 4 times 5. So square root of 4 times the square root of 5, giving us 2 times the square root of 5. And then that could be simplified, 2 and 30 into 1 and 15. Here we used a conjugate. Because there has a plus or a minus, this is a radical binomial, we used a conjugate. If this is minus, we use the plus version. If this were plus, we would use the minus version. Regardless of whether this is minus, so this is plus, or this is plus, so that is minus, regardless of that, these are conjugates. And conjugates are a plus bi times a minus bi, which means you have your first term squared minus your bi squared. Conjugates, when you multiply conjugates, the whole point is you get a difference of perfect squares. Your first term squared minus your second term squared. That's the pattern of conjugates. This is always minus. Now, with the unique properties of what am I doing? I'm sorry. This is a radical, right? So that's not an I, because that's what we're about to do. So radical B. So sorry about that. So this would be radical B squared. Okay, so we got let's say we got an A and a radical, we got just a number and we got a radical, we just got just a number and a radical, one's plus, one's minus. Okay? And this one, the radical is first and the number second, or they might both be radicals. Okay? The whole point is your first term is squared and your second term is squared. And there's a minus in the middle. Okay? So if my first term is squared, what is square root of 15 squared? 15. Because a radical squared is just the radicand. But this is not a radical. So if this is conjugates, it's going to be the first term squared, first term times itself, which is just 15 in this case. And what's the second term squared?
9.
9, not 3. 9. It doesn't have a radical. This is square root of 15 squared, which is 15. This is 3 squared, which is 9. And it's a perfect square minus a perfect square. Okay? So this squared, a squared, minus regardless of which is plus, which it doesn't matter. If it's conjugates, it's always the first term squared minus the second term, which should give you a new denominator of 6. The whole point is now the radical's dead, and you should have just a number. And up here, you don't distribute, just make sure everything is locked up, so this is 4 times that square root of 15 plus 3. And so you don't need to distribute, but you did want to see, hey, 4 and 6 can reduce to 2 over 3. Now, I go back and go over those more extensively, 1, because there were a lot of problems with those on the test, and 2, that understanding of, hey, just a single term, all I need to kill it is just the radical. Oh, here I have a binomial. I need to use its conjugate to kill it, and the conjugate kills it because the whole point is it's a perfect square minus a perfect square, and perfect squares kill square roots. Okay. Same thing with I. All you need to kill this I right here is what? I. Doesn't matter about the 2. If you multiply this times 2i, that's fine mathematically as long as you multiply the top by 2i, but why make bigger numbers than you have to? All you need to do is I over I. Okay? So if you have a bi in the denominator, then all you have to do is I over I. Okay? So what's our new numerator? Yeah? Yeah, that just means times. 5 times I, because we always put a number without a radical sign, just a number in front of the I. And on the bottom we have 2i squared. Now, we still have an I. But hey, the whole point of multiplying I times itself is what is I squared equal to? -1. Right. So what this means is 2 times -1. And the way you sort of just do it shorthand is cross that out and flip the sign. Right? If that were a -2, it become positive. It was a positive 2, so it becomes negative. Anytime multiplying by a -1 just flips the sign. So now we have, and that negative, with only the top or the bottom is negative, we just pull the negative out front. And so we have 5i over 2, negative 5i over 2. Now, of course, we want to write our answers in a plus bi form, full formal complex number form. So, what is our a?
5 over 6.
Our a is our pure real. Is this a pure real? Okay. Is there a pure real?
-1.
0. Right. There is no pure real. When we did this, all we got was an imaginary unit. So if we're going to write it in formal notation here, we have to put in a placeholder for that a. Okay? And now plus or minus, in this case minus, and we want to pull out this as a fraction coefficient. So minus 5/2, and put I right at the bar there. There's our a plus minus b I. Make sense? Okay. Now, we did one in class also where instead of having a single bi, a pure imaginary denominator, we had a complex number denominator. So, well, this is a complex number, but it's pure imaginary. Here's an a plus bi complex, say 4 minus 3i. Now, the example we did last time had just a single number on top. Let's go ahead and do one like you'll see in the homework also, where we have another complex number on top, or another a plus bi complex number. Okay. It's still the same skill. The whole point is right here, we have in our denominator, instead of just a bi, we have an a plus bi in our denominator. Okay. Which means in order to kill that whole complex number, a plus bi, then what do we need to multiply by? The conjugate, right. And the conjugate is going to be the same a and the same bi, but instead of minus, it'll be plus. If this were plus, it would be minus. So, we multiply by, and since these are full complex numbers, lock them up. And so the conjugate of 4 minus 3i is, bless you.
4 plus 3.
Right. Go ahead and lock it up, and be fair to the top, do the exact same thing. Now, with the radical ones from the last chapter, I said, hey, whatever you're multiplying by, you don't distribute. Okay? Because you want it to keep it factored because you may be able to cancel something out there. Okay? That was the reason, because you may be able to reduce. And if you distribute, then you'd have to refactor in order to be able to reduce. Okay? So with the radicals, just leave it unfactored. Leave it undistributed. Okay? Leave it factored. Okay? And then cancel into lowest terms. But with the i's, you want to go ahead and last time we had just a number here, and I said do distribute. And in this case, we got a binomial times a binomial, or complex number times a complex number. So what will we have to do? FOIL, exactly. So don't leave these unmultiplied. Radicals leave factored form. These, got to multiply them out, because our whole goal is to end up not with something that we can reduce to lowest terms, but that we can put in A plus BI form. And we can't put in A plus BI form if we have things locked up in parentheses. Okay. So, here, and if you need more room to really write it out expanded with all the parentheses and everything to FOIL, do so. Okay? But I know I'm going to FOIL these because these are two different complex numbers. I'm going to go ahead and write it here, but you can actually do the full expanded form. Just don't clutter up your work area. Go off and do it on the side, and then put your simplified version back here. So I've got for FOIL, I've got 3 times 4. My outside terms are positive, so it'll be a plus. 3 times 3i. My inside terms are both positive, so I'll have a plus. 2i times 4. And my last terms are both positive, so I'll have a plus. 2i times 3i is 6i squared. Now on the bottom I have conjugates. Remember, conjugates are going to give me whatever my A term is squared minus whatever my BI is squared. So my A term is, and it's going to be minus, and then I put my entire BI squared. Now, of course, that I squared is going to make what happen here? It's going to make it plus. But I'm just being really consistent with conjugates. Make A squared minus B squared. They make a difference of squares. Then once we simplify this. So on top, we've got FOIL, 4 terms. But this first term is a number, and this last term is also a number. Oh, wait, no, it's not. There's an I. There's an I squared, which means it was a positive 6, so now it becomes a negative 6. If it were a negative 6, it would become a positive 6. So you can combine your first and your last. You can F plus L. When you're multiplying, FOILing complex numbers, your F and your L will both be numbers, real numbers. That's your A component. So 12 and negative 6. And your O and your I will be like terms with I's. That gives you. And so when you FOIL 2 complex numbers, you will get a complex number. Your F and L are both numbers for your A component, and your O and your I are both BI's. They're both your imaginary terms, which become your second part. You'll get an I squared on the end here, which just flips the sign of whatever that number is. And on the bottom, we have 16 minus, don't forget, 9i squared. That square belongs to both. And that I squared becomes?
8.
Sorry?
Completing the 8 because it's 9i squared.
9i squared, so it becomes what? Plus?
Oh no, it doesn't. It's minus.
Minus 9, not 8. Yeah. Yeah, because this means this is negative 1, so that minus 9 becomes plus. Okay. So this is 16 minus 9i squared, which is 16 plus 9, which is 25. Now, the reason we wanted to multiply everything out is because we want to put an A plus BI form. And so this is two numerators with a common denominator. This denominator is common. It belongs to both the 6 and plus the 17i. So just like if these both had denominators of 25, we just add the numerators over 25. We can also split it apart. So this is 6 over 25 plus 17i over 25. But we're going to go ahead and write that as 17 over 25. There's our b. and our I goes right there. So it's basically, as I sometimes refer to, a two-headed fraction. And A, B, pull out the fraction in front, and I, and then before you move on, see if you can reduce anything to lower terms. In this case, no, but you should check before you move on. Okay with those? Okay. All right. And then to finish up 11.7, so we looked at adding and subtracting, multiplying and dividing complex numbers, understanding how I behaves, and understanding what the complete definition of a complex number is. Okay. And now we'll finish up 11.7 by looking at powers of I. So still 11.7, powers of I. Okay, so first before I get into I, let me just review real quick an exponent property, okay, that is super important for being able to manipulate powers of I. Okay, so if you have a base of 1, and you raise it to some power, I'll just put it in because it could be anything, okay? What is the answer going to be? 1. Yeah, it doesn't matter. Remember, a power just tells you how many times the base is multiplied times itself. It doesn't matter how many times you multiply 1 times itself, you get 1. Now, what if your base is -1? -1 times -1 times -1 times -1, however many times. What's your answer going to be?
Wouldn't it depend on if the exponent is odd or even?
Exactly right. Sometimes you'll get a +1, but sometimes you'll get a -1. Okay? Remember, pairs of negatives cancel out to become positive. Okay? So if you've got an even exponent, you have pairs of negatives. So you'll have a +1. But if you have an odd number of -1s, you'll have pairs, let's say there's 5 of them, -1 times -1 times -1 times -1 times -1. You had pairs that cancel out to positive, but then you had an extra one. And so that would equal -1. So this is true if n is even. Because that means -1 is a factor how many times? If it's factor an even number of times, then all those negatives will cancel out and become positive. Okay? However, if -1 is a factor an odd number of times, then all the pairs of -1s will cancel out, but then you'll have an extra one, and it makes it negative. So if n is odd. So you're dealing with ones, whether it's positive or negative, depends. Positive base of +1, doesn't matter what the exponent is, the answer is 1. If the base is -1, it depends on how many times that base is a factor, so an even exponent gives you a positive, all the negatives cancel out, +1, and an odd exponent gives you a -1, because you'll have an extra negative. Okay. So, now let's look at powers of I and some of those properties. And how we're also going to be using exponent properties. We're going to be using reverse product and reverse power rule again. Okay. So let's make a little chart here. Let's make I to the first power. What is that? Just I, yeah. No, I to the first power, just I. All right, so we know that one. Anything to the first power is just itself. What about this one, I squared?
It'd be I.
Negative,
-I, yeah.
negative
1.
1, yeah. So I to the first, the I is just I squared is no longer imaginary, it is a real number, -1. So we know these two. Now if we know these two, we can figure out any other one. So let's look at I cubed.
Would be positive 1?
Yeah, would it be I?
Why not?
I.
Negative I.
Bingo. Why?
Because one I is
odd.
square root of 1, right? And then once you multiply square root of 1 times square root of 1, it'll cancel out.
Yeah. You're on the right track. Let's simplify it. Even without using radicals, we can take what we already know about these, and we can use our product rule of exponents. We can break this into I to the 1 times I squared, right? Because the product rule says add the exponents. So I cubed is the same thing as I to the 1 times I squared, because 1 plus 2 is 3. Does everybody agree with that?
Yeah.
Okay. Well, what is I to the 1?
Just
I. And what is I squared? -1. So what I cubed is -I. Yeah. It's just an I with its sign reversed. Okay. So let's do that with I to the 4th. Now we know I to the 1, I squared, and I 3. There's a couple ways you can make 4. 1 plus 3 or 2 plus 2. Okay. So let's reverse our product rule. I'm going to use I squared times I squared, but you could also use I to the 1 times I cubed. Because reverse product rule, 2 plus 2 is 4. So this has the same value, but I squared is equal to so I to the 4th is equal to
1.
positive 1. Now you can keep going. I to the 5th, you could write as 1 and 4 or 2 and 3. I'll use 2 and 3, but you can use 1 and 4. I squared I know is -1, and I cubed I know is -I. So what does that equal?
Negative
Positive I, yeah, because I got two negatives. So positive I. I to the 6th, I could write as 3 and 3 or 2 and 4 or 1 and 5. I'll use 3 and 3. If you use a different combination, as long as it adds up to 6, that's fine. And I know I cubed is -I times -I. And so what does that equal? -I times -I is,
negative I squared.
right. Well, is it negative or positive?
Positive
Yeah.
I squared.
Yeah.
It's -1.
Which is -1. Yeah. Now, if you keep going, I to the 7th, I to the 8th, I to the 9th, I to the 10th, you're going to see a pattern. There's 4 possibilities, unless you have coefficients in front of any of these. And you may see examples like that, but if you're just looking at the pure powers, no coefficients, no other numbers involved, then the only possible answers are I, or 1, or -I, or -1. I, -1, I, +1. I, -1, I, +1. You're going to see that pattern repeat. Okay? So let me sum it up here. Because the basic powers you need to know are I to the 1, of course, is I, and I squared is equal to -1. Okay? I cubed is equal to -I, and I to the 4th is equal to +1. Oh. And those are the only 4 options. And if you keep going, that pattern is going to repeat. And that's the only 4 options. Now, notice the ones that are most useful to us here are whenever we can deal with real numbers. Okay? So I squared is -1 and I to the 4th is 1. Our even exponents are real. Our odd exponents are imaginary. So our even exponents, 2 and 4, are real numbers, either -1 or 1. Our odd exponents, 1 and 3, are either I or negative I. They're imaginary. And that's going to hold true because this pattern is going to repeat. Any even exponents of I are going to be real numbers. Any odd exponents of I are going to still have an I in them. So our job now is when we get into higher powers, not having to make this list and just type, go down that list and find that till we get there. But how can we get there quicker if we understand this basic pattern and what to expect? We can break bigger powers of I down into these basics, breaking it down either with the product rule or with the power rule in reverse to break it down into smaller exponents until we get an exponent that will help us. So let's say we have I to the 20th. Now, is that an even or an odd exponent? Even. Therefore, we can have a real or an imaginary answer?
Real.
Real. Any even exponents, like I squared or I to the 4th, even exponents are going to give us a 1 or a -1. There's no coefficient here that's just going to change the fact that it's either 1 or -1. Huh? Yes?
Well, like in the case of whenever you did like 6, you can just like put it into 2, right? And it'll equal that answer, like
yes.
just completely.
Yes. But the bigger number it is, I mean, we could do 2 and 10.
Or 10 and 10, and then it'll.
Yeah, 10 and 10. Yeah.
The same.
Right. So we could do 10 and 10, but 10 we'd have to still figure out our list. Or we could do 2 and 2 and 2 and 2 and 2.
Yeah.
Yeah. Yeah. Or what? Sorry. Right. Now 4 and 5 would be breaking it down by the power rule. So you're talking about doing the product rule. So some string of things that add up to 20, right?
Yeah.
So, but the thing is that the bigger number you get, you're going to have a long string of things in order to get ones that are 4 or less that add up to 20,
Yeah.
or a bigger number.
If you do it like you did the I squared, it would just be -1 times like the.
Yeah. Yeah, if it was I squared times I squared times I squared times I, 5 of those, that would be -1 times -1 times -1 times -1 times -1. Great, but the bigger number you get, that gets really unwieldy. Mathematically true, so good observation. But remember that exponents are just repeated multiplication. So a lot of times instead of using the product rule, we can actually use the power rule, okay? Because that'll kind of shorthand our multiplication. So if we rewrite this, I'm going to put a parenthesis and an I, and then leave some room. What I want to put here is I want to reverse my power rule. I want to have a power here and here, and our power rule says do what to the exponents? Multiply for the power rule, right? So we want 2 exponents that multiply to make 20. Okay? Now, what we want to put here is we want to put a 2 or a 4. Because 2 and 4 are real numbers. We want this to be 1 or -1. And which would be better, -1 or 1? 1 would be best. If we can use a 4, use it. Okay? If this is an even exponent, you can always use a 2. But if you can use a 4, then go ahead and use it. Okay? So I want this right here to be a 1 or a -1. So I want a 2 or a 4. Can I use a 4? Yeah. If 20 is divisible by 4, remember product rule says multiply, so we reverse product rule by dividing. If 20 is divisible by 4, good, we can use a 4. We could definitely use a 2, but if we can use a 4, we will. And then for this to be true, what do I have to put out here? 5, yeah.